Assalamu alaikum, madam. My name is Ayam Alvi, and on behalf of our group, welcome to the Project 2 video demonstration. For this project, we applied 5 inferential statistics methods to the Pokemon dataset from Kaggle. Of our group consists of 4 members: myself, Pritoy Roy Om, MD Hafizur Rahman, and Samiha Nur Arora. I will cover the introduction and the dataset overview. Then Pritam will present our hypothesis testing and correlation analysis, followed by Hafizur on the regression and ANOVA, and finally Aurora will close with the goodness of fit test and our conclusions. So let's get started. In this section, I'll walk you through why we chose this dataset and what we set out to investigate. Our project has 5 core objectives. First, we want to test whether the legendary Pokemon have significantly higher overall stats than non-legendary ones using a hypothesis test. Second, we want to measure correlation between speed and total stats. That is, do faster Pokemon tend to have a stronger overall. Third, we build a simple linear regression model to predict a Pokemon's speed from its attack. Fourth, we use ANOVA to test whether strength differs from all six generations. And fifth, we run a chi-square goodness of fit test to check whether the 18 types are equally represented in the dataset. Together, these 5 analyses cover all compulsory methods required by the assignment brief. Our dataset contains 721 entries described by 13 variables. 7 of these are continuous numeric stats: HP, attack, defense, special attack, special defense, speed, and total, where total is the sum of all 6 battle stats and serves as our main overall strength indicator. The remaining 6 are categorical: Type 1, Type 2, Generation, and Legendary status. The dataset spans 6 generations from Generation 1 all the way through Generation 6. It includes both regular and legendary Pokemon, making it well suited for group comparison analysis. With that, I'll pass it over to Pritam.
Hello everybody, my name is Pritam Roy and I'll now present two analyses. One is an independent sample t-test comparing legendary and non-legendary Pokemon, followed by a Pearson correlation between speed and total. So for our hypothesis test, we asked, do legendary Pokemon have significantly higher overall stats than non-legendary ones? So first, we set up the null hypothesis as the mean total stat is equal to both groups. The alternative hypothesis is that a significant difference exists. We ran an independent sample t-test using R. The mean total for the 735 non-legendary Pokemon was 417.21, while the 65 legendary Pokemon averaged 637.38, a difference of over 220 points. The test statistics was t equals minus 25.83 with approximately 102.8 degrees of freedom, and the p-value was less than 0.001. So this is far below our significance level of alpha equals 0.05. So we reject the null hypothesis. This confirms what most Pokemon players already know intuitively, that legendary Pokemon are by design dramatically more powerful than the regular ones. Next, I looked at the relation between speed and total using Pearson's correlation coefficient. The result was R equals 0.576 with a 95% confidence interval from 0.528 to 0.620 and a p-value less than 0.001. This indicates a moderate, significantly significant positive correlation. In other words, faster Pokemon tend to have higher overall base stats, but the correlation is not strong enough to be perfectly predictive. So looking at the scatter plot on the right, we can see a clear upward trend. Though there's a considerable spread at every speed level, some Pokemons are fast but weak overall, while others are slow but extremely bulky. With that, I'll hand over to Hafizu. Thank you all.
Thank you, Pritam. My name is Khandoganem Hafizur Rahman, and I will present two more analysis. A simple linear regression predicting speed from attack and one-way ANOVA comparing total states across all six generations. Next, our equation was can attack predicting speed. The regression equation is speed equal to 41.31 plus 0.34 into attack. This means if attack increase by 1 point, speed is expected to increase by about 0.34 points. The result is statistically significant because p less than 0.001. However, the r square value is only 0.145, so attack explains only 14.5% of speed. The scatter plot shows a positive trend, but many Pokemons are far from the line. This means attack is not a strong predictor or speed because some Pokemons are strong but slow, while others are fast but not very strong. Okay, next our equation was does the average total star change across the six generations? The ANOVA result is F equal to 1.57, sorry, it's f equal to 1.547 and p equal to 0.173. Since p is greater than 0.05, we fail to reject the null hypothesis. This means there is no significant difference in the average total stat between the six generations. The box plot also shows similar medias and speed for all generations. This tells us the Pokemon's strength has stayed fairly balanced across different generations. Thank you. I will hand over to Samia.
My name is Samihanur Aurora, and I will be presenting our fifth and final analysis, the chi-square goodness of fit test, followed by a summary of all findings, our limitations, recommendations, and the closing remark. Our final analysis asks, are the 18 Pokemon type equally distributed across the database? The null hypothesis was that each type appear at roughly the same frequency, that is, each of the 18 types would have about 44 Pokemon if distributed very perfectly uniform. The alternative hypothesis was that the distribution is uneven. We calculated the chi-square statistics as 220. 97.77 with 17 degree of freedom, giving a p-value less than 0.001. This is a massive test static, and we clearly reject the null hypothesis. Looking at the bar chart, the distribution is highly skewed. Water type is the most common with over 110 Pokemon, followed by normal with nearly 100. At the other flying and ice types each have fewer than 20 Pokemons. This reflects deliberate game design choices. Certain types are thematically more versatile and appears throughout all generations, while others are rare by design. The t-test showed the legendary Pokemon are significantly stronger with p less than 0.01. Persons correlation found a moderate positive relationship between speed and total regression showed the attack is significant but weak predictor of speed. ANOVA found a significant difference in total statics across generations, suggesting good game balance. Finally, the chi-square test confirmed that Pokemon type are not equally distributed with water and normal appearing more frequently. Overall, 4 out of 5 analyses were statistically significant, while the ANOVA highlighted consistent balance across generations. Our study has three limitations. First, the database includes only the first 800 Pokemon, so newer generations were not analyzed. Second, we assessed normally visually instead of using formal tests. Third, the database is static and cannot show changes over time. For future research, we recommend using multiple regression tests, testing the relationship between legendary status and type, and expanding the database to include newer generations. In conclusion, our analysis shows that the legendary Pokemon are stronger, speed is linked to overall power, attack has a weak but significant effect on speed, generations remain balanced, and type distribution is uneven. Thank you.